Welcome to another Center for AI Innovation seminar over this lunch hour. My name is Brendan McGinty. I'm part of that center, and we are thrilled to have Alex Schwing with us today. Let me go ahead and do an introduction of Alex and then hand it over to him. Alexander Schwing is an assistant professor at the University of Illinois Urbana-Champaign, working with talented students on computer vision and machine learning topics. He received his BS and diploma in electrical engineering and information technology from the Technical University of Munich in 2006 and 2008, respectively, and obtained a PhD in computer science from ETH Zurich in 2014. Afterwards, he joined the University of Toronto as a postdoctoral fellow until 2016. His research interests are in the area of computer vision and machine learning, where he has co-authored numerous papers on the topics in scene understanding, inference and learning algorithms, deep learning, image and language processing, and generative modeling. His PhD thesis was awarded an ETH medal, and his team's research was awarded an NSF Career Award. For additional information, and I'll put this in the chat, he's wanting you to browse to Alexander-Schwing.de. I'll put that in the chat. Alex, what a pleasure having you here today. The virtual floor is yours.
All right. Thanks a lot, Brandon, for this nice intro, which starts to remind me how old I am. We should probably remove the dates from this.
You should not talk about age with me, Alex.
Anyway, I intend to make this talk, I guess, fairly high level. So we'll not go through a lot of intricate math here. I leave that to the students that I'm working with and the papers. This being said, if you're interested in any of this, please just always feel free to reach out. We're happy to discuss in more details about what we're up to and what we're busy with. And I should say by we, I mean, as Brandon also hinted to, a set of talented students, which I usually call them the magicians. They're really the ones that make all this work, and they're the ones that deserve all the credit. It's their work that I'm talking about, and I'm hoping I mention the names more specifically when we get to the different works. I do also want to say thanks to NCSA, and particularly NCSA ISA, specifically Vlad Kindratenko and his supporters. They have always been very helpful in particularly getting us the computational resources that we need. Much of the results that I'm going to show wouldn't be possible without their support. And we do use quite a bit of compute resources. And also, most of our publications acknowledge their support explicitly. Now, that being said, luckily or unfortunately, depending on how you look at it, that compute is nowhere close to enough. So I do want to also thank many other contributors, Samsung, Cisco, Amazon, Facebook, Google, AMD, all of which provide resources in one or another way. And none of this research would be possible without any of these support. All right, with that being said, let me jump in. And I guess it comes at no surprise if I'm telling people here on the call that computer vision and machine learning have been remarkably successful in the last couple of years. And I would say that models which analyze, and I deliberately use the word analyze here, work very well. And you'll see in a bit why I use the word analyze as opposed to predict. Now, if you think about tasks like image classification, object detection, human pose estimation, and semantic segmentation, we have designed models in the last couple of years that achieve remarkable results. And just to give a few examples, for semantic segmentation, for instance, a couple of results here at the bottom of this slide, where you can see alternating ground truth and then the corresponding prediction of a state-of-the-art model. In fact, a model that I'm going to talk about in a bit. And you can see, if you compare the ground truth and the prediction, that the model actually makes some interesting errors in quotation marks where I wouldn't even be sure whether those are errors, right? For instance, the desk in the middle of the image, whether I call this a desk or a counter is probably debatable. And similarly, the image on the right-hand side, if I compare the ground truth and the prediction, on the ground truth, or the prediction at the very top says there's a street lamp. And if you look very carefully at the image at the very top, there are indeed a few pixels. And it is debatable whether the annotator actually forgot to annotate the street lamp here, while the model is able to pick it up. Similarly, here is yet another model, this time for video data. A model which was asked to track where are the fish moving without ever having actually seen fish. And you can see that these models are actually fairly capable of doing that right now, particularly considering the huge deformations that go into those objects. Now, this begs the question, are we done, or what is really next? And I would argue, maybe let's look at what do we really want? And one of the big goals that we're all after, I would argue, is personalization with autonomous agents. And for that, we don't only need models that predict, models that analyze, as I've shown in the past. What we want is models that can anticipate not only what is happening right now, but what is going to happen, say, a few seconds from now. To make this concrete, let's look at the images on this slide here, right? On the left-hand side, you can see the observation. And it's obviously, fairly straightforward, I would argue, using the models that I showed before to understand, okay, where are the objects? What are the types of objects? But what many models cannot do is understand, where are the occluded parts, and particularly then anticipate what is possibly going to happen. Are those kids going to step aside and yield to oncoming traffic, or are they going to run into the middle of the road without paying attention to oncoming traffic? And those will obviously lead to two totally different outcomes in the end, which we should obviously be aware of. Now, in order to do that, I would argue we need to combine the vision of neuroscientist David Marr, who argued for 2D to 3D reasoning, with the vision of famous neuroscientists Rudolf Olinath and Kenneth Craig, who said very specifically, any creature must anticipate the outcome of a movement in order to navigate safely, which resonates a lot with the research that we're doing. Now, in order to anticipate the outcomes of movements, in order to understand what is possibly going to happen down the road, we would argue that we need a couple of things beyond what we are currently able to do. And those things are specifically more holistic object understanding. We don't need to just group or partition the visible parts in an image. But if you're looking at a desk, we need to understand what is the entirety of a desk. If you're looking at a person, what is the entirety of a person? I talk about this in this talk a little bit, highlighting our work on A-modal video object segmentation. And we'll get into that in a few minutes. Beyond understanding objects as a whole, obviously we need to understand how can objects possibly move, what are likely scenarios. And for that, we need accurate probabilistic models. And we do research in that area as well, looking at stable generative modeling and structure prediction type algorithms. I will not have the time in this talk to get into that. If you're interested in those parts, please always feel free to reach out. Instead, I will go a little bit more detail into how can we devise algorithms that can actually forecast. And we have some research in this direction that I'm actually going to start up with right after this. And I probably also not have time to talk much about our research on embodied agents and the collaborative aspects. And if you're interested in that, please always also feel free to reach out. Now, that being said, as I mentioned, I'm going to start things off with talking about some work on forecasting, then getting into how can we more holistically understand objects, and what are the current shortcomings in that area. And time permitting, and I highly doubt that we will have time for that, I talk a bit about autonomous multi-agent systems, but as I said, I highly doubt we'll have the time to do that. Now, let me start with learning to anticipate. What's the goal here? What do we want to do? Now, assume you're given an egocentric image sequence like the one that is shown on the right, where you can clearly see these are 3 camera snapshots from a car moving forward while other cars in the scene are moving as well. So the observer is moving, and what we want to understand is, how does this scene evolve over time? And in very vague terms, what will happen going forward? Now, the first question we need to answer is obviously, what is a useful representation to forecast? In what way, or what is the desired output that we care about? And there has been a lot of research in that area. For instance, people have argued one should forecast trajectories, and people among this are also some of our own work, where we looked at basketball trajectories. You have some past trajectories, and you want to anticipate where are the players and the ball going to move in the next couple of seconds. But one could also make the point that trajectories are actually fairly sparse, particularly if you have the images in mind that I just showed you a few slides ago. To make the representation a little bit more rich, other people have looked at forecasting bounding boxes. And there is some merits to that, but I would argue that this is also still quite sparse. And therefore, other people have looked at forecasting semantic segmentations. Now, this is a little bit more fine-grained representation, but that representation too has some shortcomings, particularly the fact that objects are actually not disentangled, right? If you look at the image at the bottom right here, you can see all cars are mixed together, while clearly cars should be able to move independently. So maybe forecasting semantic segmentation is actually not the right thing to do either. You could then make the case that, well, maybe I don't want to forecast semantic segmentation. Instead, let me forecast individual instances. And great, yes, you solved the problem that I just talked about. But instance segmentation traditionally ignores the background, which then means you have no information about how is your background actually going to move. And yet other people have looked at forecasting the entire image. And you could make the argument that I don't really need to know the entire image in order to make the decisions that I want to make downstream. A semantic segmentation or bounding boxes or trajectories might be sufficient. And that, I would argue, is a fair point too. Now, all these representations have some advantages and shortcomings, I would argue. But interestingly, when we looked at that, I guess now about a year back, we figured out that there isn't really any work that looks at what is called panoptic segmentation, namely the fact or the combining the background and the foreground instances. And this was work that we recently published at CVPR 2021 a few months ago, which gets us into panoptic segmentation forecasting. And let me describe a little bit more in more detail what this is. Again, showing on the left-hand side the image that we just saw before, we're now interested in not only anticipating where are the individual objects, the individual car instances going, but at the same time, do we care about the background as well? And so panoptic segmentations have both thing instances and background stuff instances. So it seemed to us like a natural representation to forecast. Yet in the literature, we couldn't find anyone actually doing that. So we're wondering, I guess about a year ago, what's up with that? What's the reason? And we think panoptic segmentation is actually the right representation to forecast for two reasons. First, as I mentioned before, the observer moves, meaning the camera moves, and individual instances like things can move. And background is mostly static, while only the observer moves. Now, the nice thing about panoptic segmentation is that it disentangles both things and background stuff. And that disentanglement in traditional panoptic segmentation makes this representation very suitable for forecasting, I would argue. Again, things can move because of both the observer and their own movement, while background stuff can only move because the observer moves. Now, with that in mind, let's look at the task the way we defined it a little bit more carefully. Imagine you're given a set of images. I call them I sub 1 through I sub t, the images similar to the ones that you have seen before. The goal is to forecast the panoptic segmentation ST plus F, which is F frames into the future. And you can see that panoptic segmentation on the right-hand side, capturing both individual instances, but also individual objects. Now, how could we devise a model to do that? And I do want to emphasize that whatever you see right now on the screen is literally all that we're typically given. That's all the information that you have. You see the images on the left-hand side, and you're asked to come up with the semantic segmentation or the panoptic segmentation that you see on the right-hand side. For completeness, we overlay them with the image, but you do not have access to the image in the future. So how could we come up with that? We designed a model to do that, which consists of two parts. The first part is the things forecasting part. First, we detect the individual objects. We then sort and align the objects across the frames that we have as our input. We then have a classical encoder-decoder pipeline, which predicts where are the objects going to go. Now, the second part looks at the stuff forecasting. And it essentially takes a semantic segmentation, takes the background, it projects the background into 3D using a depth estimate. It then takes into account the observer motion, applies that observer motion H to the 3D point cloud, projects it back, does some refinement, and combining then both the things and forecasting, we then aggregate this information in order to get the final instance segmentation approach. Now, you might wonder, okay, where do we get the observer motion from? And we do consider two scenarios. One scenario, which is the active scenario, where we have the observer motion available. You could think of autonomously driving cars, which have some planning stage. You might have the observer motion pretty accurately available. But we do also consider a second scenario, which we call the passive scenario. Think about a handheld camera. There, the device typically doesn't know where is it going to go in the next couple of seconds. And we call that the passive scenario, in which case we need to anticipate the odometry as well. And we're going to have results for both cases, and I'm going to show those in a bit. Now let's look at those two stages a little bit more carefully. The things part, actually, first let me tell you how we get them. We first run a classical instance segmentation approach that gives us the foreground. You run a classical semantic segmentation method that gets you the background. And now we have pixels disentangled. And now we can look at both things and forecasting separately. Now, to forecast the individual things, note that at first, all we have is bounding boxes for each frame and possibly a representation for each detected bounding box. We call the representation R and the bounding box X. So there's R1, X1, R2, X2, R3, X3 for one frame, and the same thing in other frames. But what we don't have is, which object corresponds to this, or which objects are the same in different frames. So we need to somehow link them together. For that, we can apply a sorting and alignment algorithm, which I'm not going to talk about. This is standard off-the-shelf methods, even though at this point in time we're actually looking at improving those. And that then gives us essentially short tracks, and it tells us which detection and which representation correspond to each other across the different frames, frame 1, frame 2, and frame 3 in this case. Now, with that information at hand, as I mentioned before, you can feed this into a classical encoder-decoder pipeline. I defer all the details pretty much to the paper. We have the representation, which essentially captures what the object looks like. And we have the bounding box, which captures where the locations are for 3 frames in the past. We can encode those, then we can decode it, and the decoding part then essentially predicts where is the bounding box going to go and what is the object likely going to look like moving forward. And I skip all the details of what this representation or what this architecture does, and instead give you a bit of a high-level insight. So as I mentioned before, X is literally the location, R is the appearance, which are forecast. We then decode the appearance, that gives you a mask. You then place that mask at the corresponding location, and that gives you this black and white semantic or instance forecast of that particular instance. And that's literally all that we did for things forecasting. For stuff forecasting, as I mentioned before, take your semantic segmentations, project them into 3D, apply the transformation, project it back to the image. All this is a standard 3D projections, then refine the whole thing, and that gets you a background mask. Now, taking both the instance forecasts and the background mask together, in this first work, we did something very simple, nothing fancy just yet. We literally just took those representations, we just stacked them on top of each other. Nothing, as I said, nothing very fancy, just sorting by depth, stacking, pasting them on top of each other, and that was it. And that gets you a semantic segmentation, instance segmentation, similar, or a panoptic instance segmentation, I should say, similar to what we see on the right-hand side. Now you might argue, well, these are all very classical, very simple components, and indeed that is true. And in fact, as we speak, we're working on refining this and improving the results even further. Now, I did mention that there's 2 different scenarios that we're looking at. The active scenario, where we actually know where we want to go, or the observer knows where it wants to go, and the passive scenario where the observer has no idea what is going to happen, and the observer then needs to anticipate what is likely going to happen, where am I likely going to be? And we're going to look at both. Now, to evaluate this approach, we look at the Cityscapes dataset, which is a dataset very commonly used in that area. It consists of 5 sequences, 5,000 sequences of 30 frames. Annotations are provided for the 20th frame, and we evaluate on the validation data. We have 2 settings, a short-term setting, which has 3 frames, which predicts 3 frames into the future, which is about 0.18 seconds. And then what we call a midterm setting, which anticipates 9 frames into the future, which is about half a second. The evaluation metrics that we use are fairly standard. We compute the matches between ground truth and predicted segments. There's what is called a segmentation quality, abbreviated with SQ. And it's essentially the average IOU of matches, some classical metric. There's the recognition quality, also a classical metric. And then there is what is called panoptic quality, which is just the product of the segmentation quality and the recognition quality, also a classical metric in that area. We have a couple of baselines that we're comparing to, specifically what is an algorithm that is referred to as Panoptic Deep Lab. And Panoptic Deep Lab Oracle has access to the frame for which we actually want to predict or for which we want to forecast the panoptic segmentation, which is why it's an Oracle algorithm. We don't have access to that frame, but it's instructive to see that result because it provides an upper bound as to what we can hope to achieve. Panoptic Deep Lab is essentially just applying that very same algorithm to the last observed frame, ignoring any possible motion that could happen. And that's interesting because it provides a lower bound for what could possibly happen. We then have we also use a flow algorithm where we take the Panoptic Deep Lab result from the last seen frame. We estimate the last possible optical flow, and then we then forecast what could possibly happen. And that hopefully result is a little bit better than assuming that nothing moved. As we mentioned before, there's a couple of baselines that looked independently at instance forecasting and semantic segmentation forecasting. And we can obviously take these baseline approaches by other people and combine them in order to get a result as well. And we compare to that too. Now, let me start things off by showing you a little video. And what you see in this video is in the top part, the most recently seen input frame. That's the last frame that you have access to. And in the bottom part, you can see the hybrid baseline that I just talked about, which is supposed to anticipate what happened 9 frames ahead, and our forecast, which is also supposed to anticipate what happened 9 frames ahead. And for completeness, we overlay the anticipated panoptic segmentation with the image that you do not have access to, just such that you can more meaningfully assess how accurate is that. And I'm going to start things off with, I guess, almost like a failure case right off the bat. The car that you can see here is going to turn to the right-hand side. And obviously, there's a lot of new information that is coming in that we do not have access to. We just have this last available input frame. And therefore, the model actually has to reason about information that it does not see. And you can see if I pause here, particularly when the car turns, oops, apparently I can't pause this. Can I pause this? Oh yeah, here we go. You can see there's a lot of new cars coming in on the right-hand side of the image. The frames are barely visible. So the forecasting approach actually has no idea what to do if it has seen an object only once. It has a hard time anticipating what's going to happen. Now things start to get a lot better once, and I shouldn't go to the next slide. Sorry for that. My video control abilities are somewhat limited here. Right, once we get onto the straight stretch, things are much more stable, and the algorithm actually performs very well. Right, if you're stopping here at the intersection, you can see that forecasting straight motion of humans actually works remarkably well. And now once all the humans left the intersection, cars are going to start moving forward again. You can see initially there's a little bit of shaking of the semantic segmentation up and down. It's very hard to anticipate some of the potholes in the road. But all in all, I would argue that it's actually a pretty decent approach, considering the fact that we don't see the images. Now, to quantify the whole thing, how well does this work? Again, let's look at just a part of this table that you can see here. On the top part, you see short term, 3 frames into the future. At the bottom part, you can see midterm, 9 frames into the future. Let's just look at the all part on the left-hand side, the 3 metrics that I mentioned before: panoptic quality, segmentation quality, and recognition quality. And you can see one of the baselines, Panoptic Deep Lab Oracle, which, as I mentioned before, has access to the image that for which we want to forecast the panoptic segmentation. It provides a nice upper bound on what is actually possible with current state-of-the-art techniques. You can see, focusing, for instance, only on the panoptic quality, 60.3 is, I would argue, a decent result. If you just look at the last seen frame, it's significantly lower. If we're looking at using the last estimated flow for forecasting, the results improve from 32 to 41, which makes sense. Objects are moving. There's a lot of movements in those scenes. So just assuming everything to be static obviously doesn't work very well. Using the hybrid approach improves things even further. But if you use the dedicated approach that we developed for panoptic forecasting, you can see that results improve quite a bit, both on short term as well as on midterm. And you can also observe that the results on midterm are obviously lower than on short term, which makes a lot of sense. We'd expect the long-term or midterm forecasting to be more challenging. Now, a couple of visual results. In the interest of time, I'm going to skip all of those and get mostly to the ablation results. just showing that each of the individual components that we devised actually works pretty well. For instance, if we only use linear instance motion as opposed to our encoder-decoder motion approach, we can see that results drop quite a bit compared to the complete approach that you can see in the first row. If we use no foreground odometry, results are slightly lower. If we use different depth estimates, we get similar results, slightly lower than ours. So all in all, I would argue fairly decent approach. And we would think that panoptic segmentations, which disentangle both things and stuff, are a useful representation for forecasting. However, this being said, sudden movements are still very hard to forecast, and particularly also occlusions are quite a bit of an issue. And that brings me then to the next part of, or that really makes the case for, we don't need to only look at what we have available, we should also try to understand what is not seen. So we should start to look behind the scene. Now, I do see a question in the chat about how does the hybrid differ from your solution? Yes, great question, Tori. The difference is that we took two state-of-the-art approaches from one for semantic segmentation forecasting, one for instance segmentation forecasting, and we trained them separately on that data. And we then looked at where the instances are and where the background is, and we just merged them together. So these are two separately trained approaches, and the result is kind of post-processed and merged together. Whereas in our case, we have one framework that is trained in one go. So that's the difference between the hybrid approach versus the approach that we looked into. I'm hoping that answered your question. Cool, thank you. All right, so now let's get into, I guess, the second part of how do we look behind the scene? Now, before doing that, let me start with classical object understanding. Right? The goal is to partition an image into segments associated with different categories, like the building, the walls, the trees, the grass, the plants, and sky that you can see in this image. Now, classical semantic segmentation started probably around the early 2000s. Among the first works was work by Konishi and Yui, who used Bayesian classifiers to literally look at every pixel and classify it into the corresponding category. Now, a lot has happened in the 2000s until eventually in the 2010s, people actually moved away from classifying pixels to classifying mask proposals. And there was the mask proposal algorithms, famous ones that came up in the 2010s like CPMC. And then there were methods like O2P-RCN and SDS-CFM that were around at that time, which literally looked at these mask proposals and then tried to classify a mask into what object does it show. Now things changed essentially back to classifying pixels in around 2015, when fully convolutional networks came around. And all of us are probably aware of the fact that 2012 in computer vision, everyone shifted from support vector machines to deep nets. And with that shift in 2015, similarly in semantic segmentation, everyone moved back to classifying every pixel independently with CNNs. And that begs the question of, is that actually the right thing? And that is now some work that's literally hot off the press, just accepted to NeurIPS last week, where we are saying that per pixel classification is actually not all you should be looking at, particularly if you're interested in semantic segmentation. Now, let me remind everyone, per pixel classification is very convenient because you take the image, you feed it into a convolutional neural net of your choice, and the output you get, if you're interested in K different classes, you get K masks, and then you essentially know which pixel gets predicted as being which object. And that's very nice because CNNs are good at processing pixel, and the whole thing is very easy to implement. There's very good frameworks out there that allow us to implement convolutions and the like very efficiently. Now, in contrast, there is this mask classification paradigm, where we're interested in predicting a mask as a whole, and then attach to every mask a prediction label. Like I'm showing here on the right-hand side, there is n different types of masks, and every mask is attached a specific label. Now, the advantages of a framework like this one are that you can infer things more globally. I can look at the mask as a whole in order to identify what is the corresponding object. Also interesting is I can now unify the whole area of semantic and instance segmentation. With per pixel prediction, it's very hard to do instance segmentation. So in the community, people looked at semantic segmentation and instance segmentation as two separate tasks that were not unified. In contrast, with this architecture, we can look at both tasks using exactly the same setup, exactly the same approach, which is very convenient. Now, the right-hand side, however, comes with a shortcut, with an issue. The issue is that we now need to essentially reason about sets. We have n predictions. These are a set of n elements. Not always do we have complete n objects inside an image. So the number n essentially has to change depending on the image that we're looking at. So how could we deal with sets? And the way we did this was to start off with a very classical backbone. You have your image on the left-hand side, you feed it into a backbone, you get some image features, you possibly have a pixel decoder, which now, instead of coming up with K objects that you're interested in predicting, comes up with C channels, C layers, which are essentially just feature representations for every possible pixel. Now, to deal with sets, you might have guessed it, we are obviously going to use a transformer, which has n queries that we're going to learn. These n queries look at the image features, and then for each of the queries, we're essentially predicting which class is it, or is it no class at all, which is why you can see on the right-hand side, the n class predictions range up until k plus 1. The plus 1 is the no object prediction. In addition, for each query, we also come up with a corresponding mask embedding. And now, if you look at this, it seems like fairly straightforward already. We have n different mask embeddings. We have the per pixel embeddings. We just perform an inner product between both, and that gets us the mask predictions. And that is now a mask classification paradigm as opposed to a pixel classification paradigm. Now, the interesting thing in this architecture is that you can use any pixel level module that exists in the literature. Classical pixel level modules can be augmented, just like you can design a new pixel level modules. So you can think of MaskFormer as an add-on to any pixel level module that exists, and it transforms the pixel classification approach into a mask classification approach. Wrong direction. Now you might wonder, okay, where does this work? Now, again, the paper is already out, so you can look at it. There's many more numbers in the paper. The interesting thing is that it actually improves results by quite a bit, while at the same time significantly reducing the required floating point operations. So, for instance, using, again, DeepLab version 3 plus as a baseline, which is one of the state-of-the-art semantic segmentation results, comparing that by adding the MaskFormer on top, using the exact same backbone, we can get a plus 1.6 improvement in mean IOU on the corresponding data set. Same thing with another transformer, with another backbone, the SwinA backbone, another backbone in that area. Comparing to the state-of-the-art results gives a fairly sizable improvement, while at the same time reducing the floating point operations and increasing the frames per second at which you can process your images. This method then gives the results that I actually showed you initially. And again, as I alluded to back then, some of the ground truth assignments or ground truth labels are debatable. And if we call the desk on the left-hand side a desk or a counter, is probably up to whoever annotated these images. Now you might argue, how can all this help with forecasting? So far, this is just standard semantic segmentation, and we're not really going beyond what we actually see. And that's essentially exactly what I would want to look into now. Instead of looking at just what is visible, we want to recognize the full object, or the object in its entire extent beyond what is visible. So for instance, on the right-hand side, the bed frame or the bedboard at the top, we all know that it doesn't stop just there. It's likely going to reach all the way down to the floor. Similarly, in this case, if you look at the herd of elephants on the right-hand side, clearly an elephant is not just made out of the pixels that you observe, but an elephant is made out of much more that you can see, and there's a lot of occlusions here. Now, why is this task so difficult? Well, it's interesting that humans are actually fairly capable of addressing that task. And there have been studies out there which actually show that. However, it remains very challenging for present-day AI systems. And I would argue that there's two main shortcomings. One is it's very expensive to actually get ground truth data. And we have seen a lot of success with models that leverage large amounts of data. So one could argue, well, a straightforward fix is to essentially try to get more data. But while humans are capable of doing that, it's already quite expensive to get annotations for semantic segmentations, and it's even more expensive to do that for A-model segmentation. So we were wondering about, is there a better approach to do that? Now, before discussing that, let me also show you what do the current data sets look like. And there's essentially three main data sets in that area. There is a data set called CAII, a data set called D2S, and a data set called DICE. CAII and D2S are real-world data, but one could make the argument that they are fairly limited, nothing like what a human would typically observe. And DICE is a synthetic data set. Importantly, it just has static scenes. So there is, in common to all these, the fact that all of them are image data sets. And how can we hope to train a model segmentation from image data sets? Clearly, temporal information is very crucial in that setting. And I would argue that we learn a lot about objects by observing them while they are moving. So how do we get then a data set that has temporal information? And that brings us back now, I guess, 2 years almost, actually 2 years, where we asked exactly that question. And we constructed the semantic A-model instance level video object segmentation data set. It's a data set for A-model video segmentation. And specifically to get that data, we actually leverage games. In this case, specifically Grand Theft Auto 5. Yes, we do enjoy playing games every now and then. We use that game because it actually has quite remarkably realistic renderings. It has a whole range of different scenarios. We can control weather and lighting. So we have a whole range of different conditions. And there is ground truth annotations that are reasonably easily accessible by putting ourselves between the game and the graphics unit, which renders the scenes onto the screen. Now, that allows us to get this ground truth like the one that I'm showing in this video here, and I'm hoping the video comes through reasonably well. You can see that we can get pixel accurate annotations despite severe occlusions. And if you were to ask a human to actually get this type of annotation, that would still be reasonably challenging and obviously quite time consuming too. Here's just another example of what this looks like and the types of annotations that we can get from this. Now, you might wonder, how do we actually did this? How do we get this type of data? We use a library called script5, which allows us to control the game, changing weather, time of day, clothing, pausing the game, toggling the visibility of objects. So putting all this together, we essentially play the game for a few milliseconds, 50 milliseconds, then we pause the game. And now we're essentially toggling the visibility of objects and rendering things on the screen. First, showing the scene as a whole, then in B, only showing the objects that are visible, and then showing objects one at a time. Now, is that enough to compute a modal segmentation? Well, unfortunately, it isn't, because just comparing RGB pixels is not robust enough, right? There is shadows, there is specularities, there's all kinds of artistic effects, which make the game very convincing, but they prevent us from computing a modal segmentation. So just looking at RGB is simply not enough. Luckily, when a frame gets rendered onto your screen, the graphics processing unit doesn't only process the RGB image itself. It also has information about the depth, which is stored in what is called a depth buffer. And it also has some information about the semantic classes, which is stored in what is called the stencil buffer. And we can also extract all this information when placing ourselves between the game engine and the GPU. And we can then use all this information to essentially compare using, for instance, the depth buffer and the stencil buffer as opposed to the RGB images. And that then allows us to compute the A-modal segmentations fairly accurately. We can also get the visible masks, and we can track objects across frames, and even for very crowded scenes like the ones that you can see on this slide, we can get fairly accurate semantic and instance level segmentations. Couple of, I guess, things that I should mention is we have fairly standard annotations for it that we can extract. Let me skip the fact that we have some pose information as well in 3D. Here are a couple of results. And coming to the statistics, you can see that compared to the data sets that I mentioned before, it's a very rich data set. It has a huge number of images, or one order of magnitude more than existing data. And the average occlusion rate that you can see at the bottom right here is significantly higher than what exists in manually annotated data. And I would argue it is probably more realistic than what we see in presently available data sets. And now the question is, can we now devise algorithms to use that data set? And that is preliminary work that we're currently looking into. I'll skip how all this works because it is preliminary work, and instead show you our current results, where you can see on the left-hand side is the ground truth. Then this is just in the middle, you can see use of a classical approach. And on the right-hand side, you can see our latest results. And if you pay attention to, for instance, the legs of this person, right, you can see compared to classical results, the new approaches are more able to anticipate or to predict the missing parts. Similarly, at the bottom, some more results and some more frames on this slide here. If you pay attention to this person here, you can see once it gets behind the door, the classical approaches often forget or start to forget about the person, whereas the proposed approach is actually able to keep track of the depth. And similar thing at the bottom here, even though we can see that there is still work needed in this direction. A couple of numbers that I'm going to skip through in the interest of time. Applying that to real-world data also leads to state-of-the-art results. But that begs the question, is this A-model segmentation enough? And we're not sure about this at this point in time, but which is why we're moving forward into trying to get an even richer representation of the scene. And this is fairly recent work, just published a month or 2 months ago, which doesn't only try to get the A-model segmentation, but tries to actually get the complete mesh of a visible scene. And as you might have guessed, similar to getting A-model segmentation, we can also get that type of data from typical game engines. And then in addition to, I guess, the raw video frame, we have depth information, we have semantic segmentations, and we have object and mesh data, like the detailed one that you can see here on the right. And all of this without spending any effort on actually humans hand labeling this type of data. Just to show a couple of videos, here's a scene that you can observe from the game. And here's what the 3D of this looks like. These are the types of meshes and the quality that we can get out of this. Here's just another scene. And the corresponding mesh annotation that we can get. And here's another one. Let me skip through that, knowing that we're running short on time. Again, comparison to existing 3D data, you can see that on the right-hand side, we have a decent chunk of 3D annotations, more than 3 million frames, and many more classes than existing approaches, existing data sets have 3D models, depth data, all available. Now, in the last 1 minute, just a brief highlight of what to do with that data. And that is also an approach hot off the press, where we presented in a couple of months at NeurIPS 2021, where we're essentially using that data to now learn how to reconstruct dynamic objects. So we don't only want to get the 3D information of static objects, but the 3D information of dynamic objects. In the interest of time, I'm going to skip all about how we're doing that. That paper will be out in a few weeks' time, I hope. Instead, let me just show you and leave you with a couple of results. You can see the input sequences at the top. You can see the ground truth meshes that we can get below it, and then the predictions. And for every object that we're interested in, you can see 2 views, one from the front and one from the side. So you can see this person here is highlighted. So we're interested in only predicting that person on this frame. And you can see that person being looked at from both the front and the side. Here, right-hand side, this is even more interesting, because now you can see that the person's legs are actually missing. They're not visible in that frame, but because we're assuming a clip at the input, we can actually get the legs, and we can see the person as a whole and in a fairly detailed manner. Now, wrapping things up, this doesn't only work on synthetic data. We then took this approach and applied it on real-world data, a data set called 3D Person in the Wild. We're just given the image on the left-hand side, and you can see, compared to state-of-the-art approaches, we can actually get fairly accurate meshes out of this from just a set of images. I skip through those results and summarize by saying that there is good news in that there is quite a bit of progress that has been made in this area, but I would also argue that a lot more work is needed to really holistically understand an environment and then use it for forecasting. And this is exactly what we are particularly excited about. And with that, I'm going to conclude that I showed you some recent directions about forecasting. I talked about our directions towards holistic object understanding, and I skipped everything about autonomous multi-agent systems, which I'm happy to talk offline if you're interested in that type of area. And with that, I'm going to thank all the funding sources that made all this work possible. And I'm happy to answer any questions now or at any point in time. Just feel free to reach out. Contact information is on the slide. Thank you, Brendan. Over to you.
Alex, amazing. Grab some oxygen for a quick second. That was fantastic. I've never seen such an extensive use of imagery to support the data and the analytics. The video, just outstanding, an amazing presentation. I want to make sure we have time for just a couple quick questions. One of them, I want to make sure that Tori's that's in chat, she had asked one before, Alex, but how does hybrid differ from your solution? I don't recall you answering that along the way, but if you did, my apologies.
I think I did answer that.
Okay, yes. Very good. And then we have Xiaojia Liao. Xiaojia, are you still on? Xiaojia, who heads our data analytics team, and you know Alex. I had a question.
Hi.
Hey, how are you?
Hi, Alex. It's very interesting to hear what you talk about your other project beyond the project we are working on together. So I have a couple of questions for you. First one, you talk about forecasting, which is very, very relevant to some of our industry projects that Brandon, lead at, which I execute. So our forecasting project, just like yours, but ours is to forecast the economic data, 2D data, time series data. And we forecast like short term, which is like 24 hours, and midterm a few days, and long-term a month or something. So how do you see the similarity, or have you also researched on the time series analysis with your forecasting model?
Yeah, great question. I do have some work on forecasting with time series data as well. Some of which I'm not allowed to talk about, unfortunately. So I can't comment on the specifics and the industries that I'm looking into with that. But yes, we do have, I guess, some work in this direction. And they use somewhat, I guess early work I would argue use somewhat similar items, but more recently, even recently, I would argue there are some similarities, but there are also some differences to keep in mind.
Yes, I have a second question. The second question is, Alex, you have done so many projects, just like Brendan said, you published numerous papers. What is your most the proudest project you've done so far?
I guess I wouldn't argue. I don't want to pick out one because I think all the students that I'm working with are doing fantastic work. So I wouldn't prioritize one project over another. I do enjoy the big picture theme that I tried to outline. I think what we really care about is that analyzing data has become remarkably successful. But as I alluded to at the very beginning, I think anticipating or predicting, forecasting what is going to happen hasn't received quite as much attention just yet. And I would argue, big picture wise, that this is probably the more important task. Consider the following scenario, right? Suppose you're developing some autonomous agent, and it observes an image. It has to do its math and some number crunching to arrive at a decision. By the time it makes the decision is possibly outdated. We need to get to predict more, I guess, to anticipate what is happening in order to react faster than we are currently doing. And that's ultimately, I think, the goal that I'm personally after. And that are, I guess, the areas that many of the students that I'm working with are interested in and working on.
Jaja, thank you so much for the great questions. Alex, your thoughtfulness in your presentation and your answers, just outstanding. Thank you so much for your time today. We did go over on time intentionally so that we could fit this in. We're recording everything. It will be on our website right after, in a few days, after this presentation. And we will leave it at that for today. So thank you for your time and your attention. Alex, again, outstanding. Thank you so much.
Thanks a lot for organizing, Brandon. Thanks a lot, everyone, for stopping by. Thanks also for continued support. And if you have any questions, more technical, always feel free to reach out. I deliberately left off any math whatsoever on any of the slides.
Very good. All right. Thanks. Have a great rest of the day, everyone.
You too. Thanks a lot.
All right. Bye.